So our next speaker is Alexandre Bertails. And Alexandre is a software engineer at Netflix, working on the Netflix Unified Data Architecture and Domain Modeling Language. Prior to working at Netflix, he has held software engineering positions at Apple and the W3C, among other organizations. Alexandre will be speaking to us today on semantic interoperability at scale with conceptual RDF. Welcome, Alexandre.
Hi, everyone. Can you hear me okay? And can you confirm that you can see my screen?
Yes.
Perfect. Yeah, thanks for the opportunity to speak today. I work at Netflix. So what happened is that a few months ago, we published a blog article. So if you go on Google, look for Netflix UDA, first result would be what we published last year. I will not necessarily assume that everybody is aware of what we did there. But today, unlike what the blog article was really focused on the knowledge graph and the data movement aspect, and we are touching a little bit on the semantic interoperability as part of the article. Today will be actually a lot about semantic interoperability, what we mean by that, how we achieve that, and I decided to go into showing some actual code and commands and stuff like that. So please hang with me on that one. But before anything, I think it's still important to understand where we're coming from and why we have this problem of semantic interoperability at Netflix. So what you're looking at here is really the typical architecture for the enterprise for 80%, I would say, of what we have on enterprise side of Netflix. And it's not totally exactly like that. You can think about the world of applications and transactions, transactional systems where applications, microservices would talk to each other. Typically, they would do that over GraphQL. We do have a lot of gRPC and protobuf as well, and a little bit of HTTP and REST. But in the end of the day, the data goes into transactional stores, typically Postgres, and that's really what people are dealing with on a day-to-day basis. For various reasons, the data has to land in so many different ways in a more analytical world. There again, that might not be the best term to describe all of that, but think about data that is slower to move, but more the world of big data, indexes, like think about Elasticsearch, or even in some cases for us, some triple stores. And we have a few other databases actually falling into that world. And in order to connect all of that, it's actually not just from left to right. Like it's not just from transactional to analytical. We actually have to go back. And that's pretty typical as well. You involve some kind of data pipelines so that you can actually move data from one point to another, and you try to orchestrate all of that one. So for us, the biggest challenge really, and it's kind of we want it to be as boring as possible, is that it's too hard to shuffle data around, and it's too painful, and there has to be a better way. Like we said, talked about different kind of systems, but really the problem is not really inside the systems. It's really that in each system, we would find actually the same schema representing the same kind of entity, but just wildly different. So because of that, it becomes very, very hard to reason about what we mean by movie or talent or anything to that nature, but really anything. So my team has been responsible for middleware infrastructure to help with that kind of problems for a very long time. So here you see a good example, and we published a few articles on that. We have a graph search solution where we can actually take data from the transactional system and help other teams, like other engineering team, land the data in Elasticsearch, and then re-expose that onto the GraphQL graph, for example, and everything is connected. That's one of the many things that we've been doing. It's just way too hard for everyone involved to manage all of that. So the dream is really, can we get to that world of a pure data model expressed in a very, very pure way? You define the facts of the world, how things are supposed to be connected to each other, and then everything becomes an implementation detail. So that's really the dream. And we came up with a full-blown solution. By the way, I'm super happy that I came after a presentation from Katarina and Mike this morning, because they've really made the perfect case for the kind of stuff I'll be talking about today. I'll just be a lot more precise about how we are doing it in our case. So for us, the conceptual modeling aspects is what we call a domain model. It's a lot more precise than what a lot of people would call an ontology. And on top of that, there is that notion of context that Mike was talking about. How do we even organize things, domain models? How do we connect them to each other? And how do we manipulate them? And the fundamental thing here is that if we can actually define a domain model, there are a few ways that people can actually get there, then the idea is that we can actually automate the projection of that domain model, that conceptual model, into a variety of schemas. So at the time we wrote the blog article, we were only dealing with GraphQL, Avro, and Java. That was really the main three data representations that we were after. Since then, we've been adding a lot of them. So we do generate entire Java APIs. We have now protobuf and SQL that we can generate. Actually, Shackle was already there, as you'll see today. And a big area of investment for us is automating the creation and manipulation of Elasticsearch indexes as well to make it more automated. But once again, the idea is if someone can get a domain model into UDA, they get the benefit of all of the projections for free. So the question is, how do we get there? And first, just to make sure that everybody can understand what I'm talking about. Sorry. Okay. So I'll be showing something that is still kind of a POC, but it makes it easier for me to explain, how the domain modeling works. So that's actually a POC that we've built. It's not yet exactly in production, but the idea is that people can try to create their domain model. So typically in this UI, you would be able to write some turtle, which would be expressed within the upper vocabulary, and then you'd be able to get some transpilation from there. But instead, just to make it easier to understand the expressiveness of the language, actually we played with that visual representation. If you're familiar with ERD, entity relationship diagrams, that's very much the target. So that's actually targeting a subset of what you can do in upper, but we think it actually captures 85% of what most of the entities in the enterprise would fall into. And the way that it works, so the first thing is that people would have to say, hey, I'm actually defining my domain. So there is a first organization of all of that information that is happening in domains. It will correspond to what most people would call an ontology, but there again, it's a lot more precise. Actually, if I just change the domain name here and I go back to the detail, you would see that we have actually minted a URI for people and they don't have to think about it. But let's go back to that guy. So I'm just describing the world of One Piece. It's a very, very famous manga anime. And in that world, you just have characters, and those characters can eat some devil fruits. And the devil fruits themselves can be organized in a category of types, like three kinds, Paramecia, Logia, and so on. So what's going to happen is that people will be able to describe their entities as what we call a derived class. And I will show in an instant, in actual turtle what that looks like. And the properties, so really more like attribute, and then relationships to other things, And then we see that the notion of enumeration is actually baked into the modeling language. So concretely, one piece would become an actual ontology, but expressed in a world of domain models. In order to have access to what is the domain name, we actually have to verify that information in the model. That's not something that we can just infer from the prefix. Like prefix doesn't really exist in the RDF model. There is a notion of ownership that happens. I won't really talk about it today, but the notion of if you want to register a domain model into UDA, we still need to know who you are and who is the owner of the domain model. And we have a very loose notion of ownership at this point, which is very limited to what our team actually cares about. But then we get into the meat of the subject. So the character class, we see that so everything is expressed within the upper vocabulary, but we have something that is much more precise than what most people would call in a class in RDFS or OWL. And we get into more details there, but the idea of a dry class is that back to the idea of what Mike was talking about this morning, is that an instance has exactly one type, and that's actually the expectation for dry classes. They would have to express the type that they belong to. That makes it a lot easier to reason about something that will become like a class. A dry class would become a table in a relational database, or it would become a federated type in GraphQL, or anything of that nature. Like we can say directly where the instances are, and there is nothing in between that interpretation. You would probably, if you're familiar with Shackle, you will recognize a lot of the same vocabulary when it comes to we talk about properties. You recognize min count, max count. That's very much because we are mapping all of that stuff to Shackle eventually. But there are a few things that you haven't seen anywhere, like a primary key loosely corresponds to our ASCII. But we'll see actually towards the end that there is something much more precise there than just our ASCII. So I'll go very quickly on that, but the main building blocks of domain modeling in UDA using upper are the derived classes, which can be keyed on some primary key, then relationships to other classes. In this case, it's a relationship to another derived class, which happens to be keyed on the name as well. Then we have things that, again, actually don't really have any correspondence in OWL or Shackle, like the simple notion of an enumeration of things that's how that would be defined in this case. So we have upper enumeration, and attributes. That was pretty much the end. So let's move into something more concrete. So what can we do once we have something like that? I'm just moving to another. So it's the exact same content, but now I can actually move around. I can introspect things, and I have access to more capabilities through our CLI, and because I want to show a few things over there. So let's see. So this is onepiece.ttl, pretty much the same one as what we had before. I won't get into exactly what that means, but I think people can understand the notion of cardinality, the notion of data types, which actually correspond exactly to the XSD data types, and a few more. But what can we do with that? Well, the first thing that we can do is that once you have defined a domain model, you can actually ask through our UDA command line interface, we can say, hey, please validate that you're going to use the governing model, which is called upper. And in that case, just go find the domain model in that location over there. And yeah, that's going to be annoying. We are reworking on the that user experience actually this quarter. So there are a few kinks that we need to fix. But you see a few interesting things first. So there is a notion of resolution that happens. So that's actually related to what Mike was calling a context this morning. Where do we find the the information. So the universe is really very much the universe of discourse in our case. And it tells the system, hey, actually, I want you to go to, in this case, the file system to find your stuff. But if you're in production, there's probably a universe that corresponds to the production environment, another universe that corresponds to test, and probably some development universes. That's actually the way that we organize our stuff in our case. But we needed that abstraction in the middle that allows us to reason about when we want to talk about something, when we need to dereference something, we need to have something that can actually answer that question. So that's what we call a universe. Once we have that, so some domain models can become governing models. So that's the case of Upper. Upper is really the first of the domain models in the UDA ecosystem. And it can be used to validate other things. In this case, it's validating onepiece.ttl. Yeah, so we could try to do some. Of course, it would break very easily. I don't know, what can we break? Like if we say that. So in this case, I just removed the min count that was expressed on the attribute. But turns out the min count is actually a required property for any attribute that is being defined. And you can see here that we're actually using shackle in order to do the validation. So this is a very simple shackle report that for now we are just returning to the user. But that's actually pretty easy to customize for a different experience. And it says, yeah, by the way, for character name, so that was the thing over there, there was an issue with the min count. It needs to have at least one value. All right, so things can be validated, and that's using shackle. Then what's really interesting is now that we have one piece being valid with respect to upper, it means that we can actually use it to validate other things. So, for example, okay, so here what's going on. The governing model in this case is becoming one piece itself. So one piece happens to be valid with respect to upper, which means that now it can itself become a governing model for something else. And then here we're going to use one piece data, which is here. So we have some instance data over there, and we should be able to validate that, which is just fine. If you remember the Devilfoot name, let's go to this one. The name of the character was a required property. So if I actually remove that information, same story, it should fail as before. So Oro Azoro, which was that entity over there, is missing the character name, is to have at least one value. So that's working as expected. So here the thing to remember is that once a domain model is used as a governing model, it behaves as if it was actually expressed, as if it was using shackle, except that users don't have to learn any of the shackle stuff. It's actually a little bit too hard for them to manipulate. All right, so I think it's useful at this point to explain how that works, looking at some actual code. So don't worry, I will explain what's going on, but that makes it a little easier for me to introduce you to the concepts that were involved. And we are at a point where there are not that many of them anymore. So here's just starting with the notion of just the URI pointing to the domain model that we're looking at. And as I was talking about, I've constructed the same as on the CLI, a universe, which represents the universe of discourse. And that's really it's really capturing the context for the resolution of the URIs as we follow the graph. So in this case, it is made out of first the file system, the demo universe, and there is something that is always there, which we call Big Bang, and that's actually how we bootstrap the world of domain models, and that's what would include by default upper and some related domain models. We'll be more precise about that in an instant as well. So what we did earlier, we said, okay, I wanted to resolve one piece within my demo universe. And in order to do that, actually, you need to start with a governing model. So there's always a starting point, which is the governing model, which is bringing the context in order to do the resolution, the validation, and other things like that. So the first step for us is to resolve, like follow our nose, from starting the first URI and see how things are connected and assemble everything is what we call a governed graph. If you want to think about that as a RDF dataset, that would be okay. But again, it's a lot more precise than just RDF dataset as you would see in Sparkle or RDF, more recent RDF version. But what's really important is that the governed graph would not only include the things that were resolved and connected to them, but it would have as well a handle on the governing model that led to the resolution. So that means that for us, it becomes from the governed graph, we can just call validate, and the right shackle validation would actually happen. There again, there's a lot of information, a lot of information architecture which is at play. Where in shackle, it's like very hand wavy. There is a instance graph, a data graph, and there is a shapes graph. It's actually very hard to connect them to each other if you've ever played with shackle. And this approach here is actually aware of all of the name graphs which are involved. So now we can actually do some more advanced stuff. Actually, that was a requirement for us at some point to move to such an approach. Then the second part was once I had the one piece domain model, I wanted to use it as a governing model. So that's what's happening here. So just like above, first I'm resolving one piece into a governed graph, but then if it happens to be valid, we validate it manually on the CLI, then I can try to promote the domain model into an actual governing model. So that would be the same type as that governing model upper here. But now I gave the capability to another team, the one piece team, to actually own their domain model and governing model. And now they can do stuff with that, like validating their own instance data, which is exactly what's happening here. So you see the one piece data.ttl here. We just lift that into a name graph. Then we can do the resolution of that thing. And same as before, now we can validate the instance data for one piece against the one piece ontology. We had a look at the breaking data that is invalid with respect to the domain model, but we'll be able to test that like that. It's pretty much the same thing. And all right, so now the next pretty cool thing, which is happening, is that. So back to this diagram, right? Given a domain model, we've seen that we can actually generate a Java API on top of it. And that's actually what we can do for one piece. So for example, I will just put the one piece domain model here so that we can compare things. And then you'll see that over there is a class, one piece character, which happens to be there in Java, which is a typed language. And if I were to open it, you would see that it says, hey, I've been generated. Actually, I've been generated from that one piece character thing, which is over there. So it seems like we have the capability to go from the definition of a domain model into something that can be executed like for real, like we have an actual Java class that we can use. And so in that case, the Java class will become a normal Java concrete class. All of the properties, attributes, and relationships would become, so in this case, we see one piece character name is the one that is coming from that attribute over there, mapping the XSD string to a string and so on. And if you look at we generate a lot more stuff now. That's pretty cool. Yeah, we used to have only the getters, but as of last week, we have the setters in place. Just seeing that live. Yeah, so somewhere in there should be a getter to go to the devil fruit. I just don't see it, but it has to be somewhere in there. So that works, but what does it mean? So if you know Jena, which we are using, it allows us to do something like that. So we can resolve essentially any RDF graph using Jena, normal Jena. And then what's happening is that the Java classes, the Java API that we generate is using the Jena personality framework, which very, very few people know about. But it's actually a gem within the Jena framework. And it allows us to do something like that because we can say, all right, I've done the resolution, so I'm still getting to my governed graph just like before. I can validate or whatever, but now what I can do is I can equip my resolved graph with a Java personality as in a set of facets. So I can now navigate my RDF graph using pure Java, like an actual Java API. Which is happening here. So the way that it works, we automate all of that. Say, okay, just equip the RDF using the one-piece domain model. And now, if I focus on, let's say, that entity over there, within that graph, I can say, please apply the facets. And now I should be able to manipulate that node in the graph as if it was a one-piece character, which is the case. So now I can just follow the links and I have access to whatever is interesting in there. All right, so let's take a break. So that's what we've seen so far, right? And I wanted to, so yeah, show, don't tell. That was the feedback that I was getting. People thought that it was a little bit too magical what we were pretending we can do in the, from the blog article, but I wanted to show no, that's actually working and it does so much more than that. And I see that Larry is in the queue for a question. Please go ahead.
Yeah, I'm curious. The stuff you're showing, are the business unit experts or the consumers of this, are they working in that turtle on the left in this IDE? And you're not exposing or what is the business user who's using this C in their interface?
Yeah, great question. So we touched on that in the blog article. The question is, there's probably arrows that are missing. How do I get to the domain model? So for now, the PDM, Primary Data Management System, is the main user of our system of UDA at Netflix. They are highly motivated. And yes, in their case, they are using Turtle as the way to express everything. So that's one aspect. We are seeing more and more actually of people who see enough of the value that they learn enough Turtle and they use our tooling to onboard in there. And we are making that easier as we speak. Like there are people working on that. Now, there are two more things that I need to mention. So one is we have another initiative. A lot of that stuff is to productionalize domain models in Java applications. And there is a desire in that world to be able to author a domain model inside the Java syntax. We think it's actually interesting. So that other team is actually working on that alternative syntax. At the end of the day, it doesn't really matter for us. Like Turtle is just a native way of writing the domain model. But at the end of the day, it's RDF. Like there is a domain model that tells you what a domain model is supposed to be. As long as it's valid according to that, we are good to go. So one, some people are motivated enough. Yes, they're writing Turtle. Two, we don't care actually about the actual way to author the domain models. In fact, we are looking into Java. And three, which is actually probably the most important is there are many cases where we can start with actual schemas that exist, which are deployed, especially in GraphQL. And we are working, it's pretty much done at this point, but we're working on extracting the domain models from existing schemas as a way to bootstrap the knowledge graph. So if you take GraphQL for us, that means all of the investments that we've done in GraphQL so far on the enterprise side, think about hundreds and hundreds and hundreds of federated schemas. They exist in UDA, and they would be usable by anyone as soon as we iron out a few of the kinks there. But that's actually where we see most of the value, which is let's reuse what exists and make that available in a way that is actually correct. I'll take one more question, and then I have a few more things to talk about. Michael?
Yes. So you've got a lot of use of turtle, so and RDF, so you're using triples. Are you using commercial triple stores or your own graph database?
It's a good question. So for the turtle, for example, that is, so if you go in, it's annoying. If you go in there, that turtle, for example, there was one property here, which is if you happen to use turtle and you go back to that UI, you spent a lot of time writing your turtle in a way and you want to get it back. So for that primary store, we're actually using mostly a key value store where we can actually store the actual turtle. So in that case, not a triple store for the primary store. We store the actual turtle when it happens to be turtle, because the users want to get back what they wrote. So that's one aspect. Then there's another aspect, which is, well, turtle is all good and fine, but in order to be able to query the connected data, the actual RDF, we actually inject all of that data into Neptune in our case. That's really our primary store at the moment. But I want to be clear for what becomes actual RDF triples in UDA, that only includes the domain models. So think about hundreds, like thousands of them. It's not super, super big in that sense. Plus, that's better explained in the blog article. So we have the domain models, the concepts. We have the data containers. So, for example, we want to know that there is an Iceberg table over there. So the coordinates of that Iceberg table in the big data warehouse, plus a representation of the schema. So we do that for Iceberg. We do that for our data mesh solution. In that case, we're using Avro, plus again, the coordinates and so on. So that's what we call data containers, locations plus schemas. And then the third component of the actual knowledge graph that actually becomes triples and ending up in the Neptune are the mappings. And the mappings are exactly what they sound, the ability to connect the actual concepts with the data containers. So that's very important for discovery, because now someone can go into UDA and say, hey, I've heard about that movie entity, but I'm actually interested in where it's getting materialized in the big data warehouse. So we would be able to, to allow you to search for the entity, and then through the mapping, we can say, okay, it exists over there and over there and over there. Which one are you interested in? And that's as well important for the data movement aspect of what we do. Before a better answer for that, I would redirect you to the blog article where we get into more details for that.
Thank you.
All right, so I wanted to be actually more concrete about the transpilation aspects and getting closer to the notion of semantic interoperability and how we get there and what does it look like at the end. So, and I would show you. So we have one piece TTL, which is valid. And in this case, I'm using just another capability, which is the transpilation to GraphQL. So first, I will just show you that it works. Again, we are not lying. So it just spit it out for that very simple domain model, some GraphQL. Don't worry about reading that because I will actually load it in the IDE that make it easier. But I will show that we can transpile to Avro the same way. Looks like that. All right. So now with that being said, let me show you in that view a few interesting things there. So that's the exact same output, just easier for me to show around. And I will open the Avro version of it. And I will make them I will have them side by side. So let me find, all right. So left-hand side, the one piece character joy class. On the top here, we have GraphQL. So you see one piece character again, but this time as a GraphQL type. And then in Avro over there, you see a record again for that one piece character type. But in that case, in one case it's a record, in one case it's a type, and here it's a direct class. So there is an intuition that, okay, these things are related. And not only they are related, but they are physically representing the same thing and connected to each other. And as we generate the schemas, and other tools would actually discover the schemas and like the data catalog or something like that, we want a way to say, hey, by the way, if you want to understand where that's coming from and what that means, that's actually directly derived from the domain model that was generated over there. So we have this notion of a UDA URI. Think about an annotation that we can actually put on pretty much anything in a schema language. So in this case, Avro over there, or in this case, the one piece character here would have the equivalent as a directive in GraphQL. So these things are the same, and we do actually remember that not only in the schema representation, but in the knowledge graph when I was talking about, what that means is that we can parse the schema. We can actually have a representation of the schema as RDF, goes into the knowledge graph. That's part of the data container. And then the mapping would be able to connect everything. And that's really the proof that we can actually navigate in between the elements between all of the schemas representations and the actual conceptual representation. And that's really what we mean by semantic interoperability, is because these things semantically are the same. And that's very different from the kind of semantics that RDF people usually talk about when they talk about semantics. For us, we use RDF as a conceptual layer in order to connect things across data representations. And that's really, really what we care about, not necessarily seeing everything as a triple. The triple is most of the time not what we care about. All right. So moving on, I wanted to show another thing that we've solved actually from day one, which is the modularity aspects in UDA. So let's say that somebody wrote their domain model one piece, and somebody wants to say something else about the characters. Like, I want to say, for example, that the characters might actually belong to a crew, like a pirate crew, and I want to give them the name. So in RDF, it's actually an issue. It's too easy. Like, just say whatever you want, and then it's part of the graph. But that's actually very, very hard to reason about. And in terms of enabling another team to say something else, something new, but something that already exists, that's actually a problem. Like, there is no good way to even talk about that in any of the ontological languages that are out there. So let me show you how we do that. So I have a very simple example of a domain model crew, which would actually import, extend one piece in that case. So it's really, it's about saying, okay, I come in, I don't need to go back to the domain owner for one piece and ask them to change something, and then I impact everything. Like, they exist on their own. That's another organization. They did all of the hard work of exposing key identities for everything. I should be able to come in and say, hey, I want actually to define a new concept, like a crew member, which will be defined as an extension to the one piece character class, and I want to attach a new property to it. And that property will be a crew name, doesn't really matter. But that's really important. Like, people in the SQL world, they do that all the time. They call that extension table. And that's a normal thing. Again, no good equivalent in RDF. You can emulate that, but it's really hard to talk about it. Same thing in GraphQL, right? In GraphQL, there is actually the notion of extension as well, which is baked in. As a matter of fact, I can show you what that would look like in GraphQL. So you see that, actually, let me move crew over there, make it easier to see. So crew member itself doesn't become directly like a term in GraphQL. It's because in GraphQL, the way that extensions work, they are more like an instruction to extend an existing type. So you would see the existing type, one-piece character being extended with a new field in this case. And that's actually something that we can then register automatically in our GraphQL gateway. And then the team who is behind Crew would be able to provide and expose the resolver for that data, or they would be able to create the corresponding Iceberg table where they would only add, that one column about the crew name. So that's how we solve the extension, federation, and modularity. All of those things are exactly they mean the same thing for us. But that was actually very important for us to be able to handle that. I will pass on validating the extension. You trust me that the transpilation works. The last piece that I wanted to show is inference. So there is something interesting that is going on here. So it's actually, if you were to look at that data here, and you wanted to really explore the data, and you wanted, for example, to say, okay, I can zero in on one piece as a domain model, and now I want to ask about all of the concepts that are defined by that domain model. That's a very natural thing to do. It's actually very hard to do with most, like if you take OWL or whatever today, there's no guaranteed way that you can do that. Like, how do you connect things? Like, usually it's because, hey, something was defined in the file where that ontology is being defined. So by convention, it's probably part of the same ontology. That's not very RDF-like. Like, you want things to be connected. As a matter of fact, if you go to the definition of domain model, just getting ahead of what we're going to talk about, the domain model would say, well, actually, I'm connected to a set of terms, a set of properties. So if that happens, I would expect actually that the domain model to say explicitly, for example, is defined by one piece, something like that. So we used to require that. There was actually and a lot more data. Then that was making the authoring experience way too hard. So even though we were not super concerned about the user experience, the authoring experience for a while, that was too much for us. So we started using inference, shackle inference. I wanted to show a little bit how that works, where we don't want people to write anything like that. We take care of that for them, and we can generate something like that. So in the end, that's what the system would see. They won't see just the data that was authored. They would see a lot of stuff that would be inferred at the same time. Let me find the character. So that's the character here after we've run some inference on it. So you see that there are a few more things, and you would find the connection between the character and the domain model, for example. So now that makes it very, very easy to either through the Java API, the GraphQL API, or the Sparkle interface to ask, hey, give me all of the domain models and their concepts. And you actually query the graph. You don't do anything weird to actually infer that information, to extract that information. Another thing that you see happening here, just showing that very quickly, that you see now the shackle stuff appearing, and that's happening automatically. So anything that is being authored in Upper actually has automatically, it lives in the shackle world at the same time. And there again, nobody has to do anything. It's just happening for free for everyone. Yeah, I won't say too much more about it. Just wanted to say that we have a little piece of inference, and we call that enrichment because we actually didn't want people to be confused with the kind of inference that people do with shackle rules or maybe entailments and reasoning. We just call that enrichment, just to be on the side. All right, so I still have a little bit of time, and the last piece that I wanted to talk about So we've seen that. We've seen a little bit, yes. So we talked about how upper itself is a little bit different from RDF, right? RDF, I keep saying that's a slide that I've been reading many times. It's important. RDF is about anybody can say anything. That's cool when you're on the web. That makes a lot of sense. The problem is that if you can say anything, it's very hard for me to understand what you wanted to say. And upper actually reverses that, the way that it works, because now with upper, you have to mean what you say, otherwise you won't be valid. That gives us a way to do governance per domain model, which is very important. So I can govern your domain model if I'm a UDA. But now, if you're part of UDA with your domain model, you can govern your own instance data. So we have a way to delegate the governance to other domains. That's the first thing. But because we require you at the first level to be an actual domain model, we can give you something very important, which you care about, which is semantic interoperability. And I guarantee you it does resonate with everyone interacting with UDA. So everything worked well. We talked about federation and inference, but there is a last trick that I wanted to talk about very quickly, which is everything that we've seen so far. We said, well, if you have a domain model, then you get all of the projections for free. And we've seen that with One Piece, and we're able to get to the GraphQL API, to the Avro schema, to the Java API, and so on. But there is something interesting which is happening. And if I go to upper itself, upper happens to be a domain model itself. That has very profound consequences, because that means everything that I showed you that applied to One Piece actually applies to upper itself. What that means is that, well, in theory, I should be able to get the GraphQL API in order to manipulate upper domain models. Well, it turns out that's exactly what we use. So here it is. That's a very big file. Actually, my IDE has some issues loading the GraphQL schema because it becomes pretty big there would be no way that by hand would be able to write that. But that's entirely generated, and that's actually what's being used by the UI that you are seeing here. That's actually using the GraphQL API, which is directly derived from upper the domain model. That GraphQL API, right, it's only a schema. Well, if you have only a schema, you're still missing the implementation, where the implementation is the same as the Java API that I showed before. So for example, I can try to go to upper domain model, and here's the actual Java class that is generated for upper domain model, and then we can just bind it with a GraphQL schema that we've seen before, and that becomes the fully implemented GraphQL service, which is powering the UI and actually a few other things as well. There again, I can guarantee you there is no way we can actually write that by hand or maintain that by hand. As a matter of fact, you can see what it looks like over there. So all of those classes, and there's more than just upper, are being generated, and that's what we ship in production. So I think it's not just cool, it's actually very important to do things that way. There are profound implications with the very knowledge graph as well. The fact that the metadata for the knowledge graph is governed by itself and everything is connected, that makes it a lot easier to reason about and to do other things with that. Which, if you want, if you really need to trust me on something, that means that the following should work, right? That means that upper itself should be able to govern itself. And in this case, upper doesn't exist in isolation. We have an axiomatization of RDF, RDFS, R, shackle, and XSD into upper. And upper, as a governing model, should be able to validate all of those things. Otherwise, we'd be in trouble. Like, we cannot really bootstrap the governance chain unless that is valid. And then you see here, each of the governing models are being validated against upper one by one. And you see that they are following each other, that they are referring to each other. And the last piece that I will show will be for Mike, based on what he was talking about this morning. So you see that all imports, and we're talking about how it's actually hard to understand how that all imports is supposed to be processed. So let me show you. I will open r.ttl, which you can see is defined as a domain model. I will go to all import, and the trick is that thing here. So we have a special annotation for some predicates, which Upper will actually look for, like for any governing model. Any governing model can actually come in and say, hey, by the way, if you try to resolve something using me, first look at all of the follow your nose predicates. And for each of them, that will be an instruction for you to reach to the other name graphs that are connected and get to the actual resolved graph and then the governed graph where everything is connected and can be validated. So that's very extensible, and we use it for other things as well. Like, for example, the mappings themselves, the idea that a mapping needs to follow the connection to the concept and needs to follow the connection to the data container is happening using the same mechanism. There is nothing that is hard-coded in the entire system. Everything is actually derived from the governing models themselves.
Are we looking at the domain model for OWL right now?
Yes.
Thank you.
Yes, that is very quickly to prove. Oh yeah, I need to do that. I need to do that. So earlier I talked about that Big Bang governing model, which bootstraps everything. So that would be all of the domain models that we ship automatically with UDA. Some of them are external vocabularies that have been axiomatized in Upper, but they will still have to be considered fully fledged domain models. And then we have a few internal ones, depending on what we need to do related to UDA itself. But that would include Upper as well in there and a few other things. So yeah, all of those things are, yeah, there's been a lot of work to make it work. All right, so that's pretty much what I had. Let me finish with that, and then I can take a few questions. So it's very, I cannot stress enough when people are trying to attempt such a thing. I mean, we spent a lot of time extracting and defining how it should work, and we landed on a set of foundations that are actually very important, we believe, to such a system. And really, that's all of them here. So the idea that Upper actually define what a model domain model is, and in particular, define what a domain model is not. That is not something, that is not a notion that exists in OWL, that is not a notion that exists in Shackle. Like saying, yeah, this is not an ontology. Well, for us, that's actually very important to reject things that are not actual domain models, because only domain models can be transpiled. Like think about a Java program that doesn't type check. You won't be able to compile it into bytecode. It's exactly the same concept here. You need to have very good foundations in order to do that. Then the other thing as well, the second one for the self-referencing, that's actually more related to the knowledge graph itself and the fact that there is not something that is out of band or outside of the knowledge graph that will give you the semantics that are missing. Like everything is inside the knowledge graph and everything is self-defining. Self-governance, there again, in order to bootstrap the governance chain, we have to make sure that things are valid. Otherwise, we won't be able to get to the API, like the derived API, the derived GraphQL schemas, and so on. Like there is no service if things are not self-governed at the very beginning, at the very top. And then the last part, which is actually almost more important than the other three, that everybody actually forgets, the federation aspect, the fact that we are able to start with a small, what I would call an actual upper ontology, but I know that a lot of people on this call might actually disagree with the definition. It's really the simplest, smallest self-contained ontology, which is able to define itself with the three properties that are above, but yet anybody can come in and extend it safely. And that's very important. The first part is answering the question, do we have enough expressivity and in the language itself, because if you can define yourself within yourself, okay, I'm powerful enough to do that. But then if you need something else, and it's very philosophical, right? It's the something else can be for Upper itself, or it can be for yet another domain model. There's no distinction that should happen, really. So that idea of you can define your own domain, I can define Upper as my own domain, and then you can come in, you can say more things safely without changing my definitions. That's actually a very important property. So that's my last slide. Yeah, so that's what we call conceptual RDF. We started talking about it like that because we had way too many people asking us, so how many triples do you have in your triple store? Well, that's the interesting things. We don't have that many. Most of the instance data still resides in other places, and it's only RDF conceptually, but it's not actual RDF. And we can, if we want, actually lift everything into the RDF format, but that's not really the point, at least at this point. The point is, why do we go with that conceptual RDF formalism? Is because we can get to semantic interoperability, like that ability to move in between the data representations is what we care about. Like we are not trying to collect everything just in one format. It's more about making the data available in whatever representation that makes sense to whatever team is working with that. Decentralized governance as a core principle of the entire system. And then the trick that makes it all work is it's domain models all the way up or all the way down. But because we end up with Upper, it's probably all the way up. That's what I had. I don't know how much time we have for questions, but otherwise you can reach out to me on my professional address, and I'd be very happy to answer questions.
We have about 4 minutes left for questions. So I see Michael has one. And Larry, oh no, Larry's clapping his hand. Michael.
Yes, thank you. So a couple of questions. One of them, it seems like this project has been going on for a number of years. Would that be accurate?
That is correct.
Okay. And also, so you're going to have had some big wins and a lot of it's operational, it sounds like, right?
Yep.
So what would you say the big wins are? And what are your next steps? What are you working on? Are you going to continue this project?
Yeah, good question. So the first big wins that we had is related to that taxonomy system, primary data management system, which is briefly described in the blog article. But it gives the ability to the business to define, there are some very important domain models that they want to make sure exist everywhere in the business. A good example is region. And so finance would come in and say, we have this definition of that region taxonomy. It's actually pretty complex, and there is data at the leaves. And we want to make sure that all of Netflix is using the same definition with the same data, whether you are a UI developer and interacting with a GraphQL API, or you are an analyst working with a big data warehouse or whatever. So with that PDM system, they have, which is built on top of UDA, they have the ability to define their model and data in one place, and we can actually take care of distributing that data with faithfully, semantically the same data everywhere. And we have a few examples like that, and that was really something that didn't exist before, and that was the original motivation. So now, where's this going? We are seeing a lot more and more use cases where people want to generate many data representations all at once from within their like projects, like Java projects, essentially. So there's a lot of work that is put into that. So more transpilers and more plugins for the Java ecosystem. That's a big one. And another big thing as well is redoing some of the tooling that my team was doing, like the cross search indexing, for example. So there is a lot of work. Now we say, okay, if you have the domain models, you know how things are connected, that should be a lot easier for everyone to define what is the GraphQL API, what is the data mesh source, what is the Elasticsearch mapping that needs to exist. We should be able to automate all of that for them. And that's going to be a big win when you know that there are hundreds of such pipelines that exist at Netflix. So that's the big things that we are working on right now.
Thank you. This is a really good presentation.
Sure.
More questions? Okay,
Oh, sorry, I had one. I'm
Oh.
just slow to hit on my unmute button. So the one interesting thing that, like as I alluded to this morning as well, that we sort of strive to at least have some level of virtualization. But I'm wondering if you have any thoughts on the impact that has. Let's say, like one of the things I would like to show off is to say, hey, if you're using, let's say, RDF OWL, it becomes much easier to hook up an LLM that can, and that will write Sparkle queries and things for you. But I'm not sure about the extent. I know we've had some internal discussions on it. Say, oh, we just use MCP and plug it in all over the place. I'm just wondering what the extent to which you might think the RDF materialization is a necessary prerequisite for those kinds of, LLM writes a Sparkle for me and retrieves the data.
It's a great question. I would recommend everyone to go on Google and Google for Netflix graph search. We just published actually an article which is giving part of the answer there. How do we use LLMs to drive that kind of questions and answers? Currently there is no direct integration between what the article is talking about and UDA, but anybody in this forum should be able to tie things together and see where that can go. I won't be able to say much more than that. Netflix graph search, and I think Larry actually, yes, that's the one.
Oh yeah, I think this was referred to me earlier, but I had not yet
Yeah.
read it. Thanks. Bill.